Okay. This was the intended title, but probably after preparing it, I think that if it turns out to be like this, then you or your students or anyone that wants to learn more about the subject that we've been talking about in this afternoon, computational complexity theory, there'll be this summer school, the Park City IS summer school will be on this topic next summer, and hopefully some information will be available about it in September in the homepage of the Institute. Okay, so as is clear from the new title, I'm going to give you some kind of roller coaster tour through the some of the ideas of computational complexity. It's good that some people talked before me, Peter and Sasha, and also Michael Rabin will talk after me, and there'll be some of the information will be completed. I think that if you want to explain computational complexity to mathematicians or to anybody in the street, in fact, yeah, so as in previous talks, the comments are on the responsibility of those who make them. You know, we have a very intuitive notion of complexity of functions. I mean, we learn this in school first, and only later we learn about multiplication. And so we know, we understand that multiplication is somehow more complicated than addition, and then later we see that this problem, determining if a number is prime, is even more complicated. And when we try to factor numbers, we really get into trouble. So in computational complexity, we try to, of course, quantify all of this, and you have seen already definitions. I'll be brief. We are interested in computing functions on the integers. Of course, pairs of integers can also be encoded as integers. And the right way we want to look at it is actually a function on binary strings. And maybe the first important observation that was mentioned by Sasha already is that we want to look at it asymptotically. And there are two things here. One is that we are going to think of each function as actually a sequence of functions, one for every input length, so n. And the second is that we are going to study this sequence for each n. We are going to look at the worst case behavior most of the time. So this C of f will be a sequence of numbers that somehow capture the complexity of the function. I will not define it here formally. It can be the complexity on some models, Turing machines, Boolean circuits, and so on, which are all essentially equivalent. And the most important choice that was made is that we are going to restrict ourselves to feasible or easy or efficient computations, by which I mean that these functions, these sequences, grow like a polynomial in n in the input length. And once we do that, so we can look at the complexities. We can study the complexity of specific functions. We have linear time algorithms for addition. For multiplication, what we learn in school is quadratic, but we can do a little better, but still not in linear time. We don't know how to do it in linear time. Primality, there is an almost polynomial time algorithm, n to the log n. But in fact, you all know that there are efficient probabilistic methods to determine primality. So the randomized complexity here can be brought down to a polynomial. And if GRH is true, then, but do you know that? I know you are working on it. And with or without GRH for factoring integers, the best algorithm we have is exponential in the input length. So this is something that so far we consider a hard function. We don't know how to factor integers efficiently. As Sasha again mentioned, another important thing that we do in computational complexity is that we bunch up problems in complexity classes. So we try to collect them into the smallest world they fit in, into the smallest class they fit in, from the point of view of some computational resource. Most of the time, and what I'll be talking about today will be, the resource will be time, but sometimes you look at problems that have memory-efficient algorithms, and this class is called L or NC, etc. We will not talk about this. The class P of problems that have deterministic polynomial time computations like addition, multiplication, sorting, etc. Lots of other problems, lattice basis reduction. Then we have the class above it, the class RP of those problems for which we have fast probabilistic algorithms, like primality testing or testing whether identity of polynomials in many variables holds. And then above it, we have the class NP that was already defined, and I'm sure people here are familiar with, in which we know lots of interesting problems, only that this class is a class that is defined essentially by problems for which we have efficient verification procedure.
So RP the set where the running time is random, or where you stop, or where the answers?
Yeah, I will not get into the distinctions. There are actually quite a few classes here. But one way to think about it is that you run for a fixed polynomial time, and there's some small probability of error, let's say 1%, which of course you can reduce as you want. So here we have the satisfiability that Sasha mentioned, the graph isomorphism, 3 coloring I'll define for you, and of course the discrete logarithm and factoring problems that were also mentioned. And even above it, we have some problems like computing the permanent of a matrix that I hopefully will mention at the end. But anyway, we try to put them in as smallest class as possible. And we have this is a picture of our world. This is the way it looks like. The containment here that are obvious from the circles are trivial. And the only thing we don't know is whether these containments are proper or not. This is the basic question of computational complexity. We don't know that any 2 classes here are really different. Maybe this collapses all the way down to here. But the choice that I talked about was that we consider everything that has, we already know polynomial time algorithm, maybe probabilistic polynomial time algorithm, feasible, and the rest we don't. We try to figure out whether, for example, factoring is hard or not. So that's a major question of complexity theory. Now, the way in which I have chosen to sort of demonstrate to you why the computational complexity point of view of the world is interesting is actually to talk about what happens when you take lots of natural notions, some of which existed much before computational complexity came to be, and you look at these through the computational complexity eyes and see what you get. And these are, notions that well, computation is clear that we want to play with that, but the notion of randomness, of entropy, questions of cryptography, secrecy, trust, fault tolerance, the definition of knowledge, what it means for a machine to know something, for example, learning, what it means, the piece of meat that Misha was talking about, and of course, as Sasha already have demonstrated, we love to play with the notion of proof. Actually, we have lots and lots of interesting definitions of proof that differ from the classical one. And the point I want to make is that when you look at these things through these eyes, you can make interesting definitions of them. And these definitions illuminate each and every one of these concepts in a new light. Sometimes it's totally fundamental. Really revolutionary, like happens in the sense of, in the case of cryptography. And I would argue that at least in each one, it adds some new dimension that people didn't consider. And so it's worthwhile. So I will talk about some of these, but the sort of focus of the statements I will make about these notions, or some of them, those I'll talk about, will be through a particular lens, and this lens was already, I guess, brought forth in the previous 2 talks, how to destroy the financial system. So it's, as I said, the basic question we don't know how to solve is to prove that something is difficult. We don't know that P is different than NP, or we don't know that factoring is hard. So what I want to see is what happens if we take as an axiom, we add to mathematics this axiom. Okay? From the rest of the talk, this is an axiom. We don't know whether it's true or false, so we can add it as an axiom. Or it may be independent of set theory, of course, we don't know. Yeah? It's not polynomial, let's say, yeah. And we'll see what happens to, no? I want to add this one. And let's see what happens if it's, under this axiom. To this. You get lots of interesting theorems, okay? Feasible computation cannot simulate nature. This is evident from Peter Shorstock, so I will not get into this at all. Computational randomness, like these probabilistic algorithms, are much weaker than you think. Yeah, this is only assumption. So all of these are theorems. So let me say even before I state them. Yeah. Let me say even before just reading them out loud, that these theorems are theories. I mean, you have, using computational complexity, you give meanings, you give formal mathematical definitions to these concepts. And once you do that, these become formal mathematical theorems, not interactive proofs or anything like this. These are, your favorite mathematical theorems, but you can see already that they have deep philosophical and scientific content. They are not just, that entropy can be deterministically increased against our intuition, that every cryptographic problem, and maybe I'll talk about that, has a solution, has a secure protocol, that every statement can be proven in a zero-knowledge way, in a way that reveals nothing about its proof, that efficient learning of concepts, as we do about tables or cats, etc., is impossible about some other natural concepts. And as Sasha got to in the end of the talk, that we use these complexity classes to look at our own work and try to understand why is it so difficult to prove things like this axiom. And we discover that, in fact, under this assumption, we cannot prove such theorems using the tools that we have been using so far. Well, let's see. Yeah. So, of course, believe me, I will have no time to define formally even one, or maybe one of these notions. Yeah, this at the end it's feasible proofs. Yeah. No, feasible in the sense that Sasha talked about. Okay, so I mean, if you look at this, what does factoring has to do with any of this? And of course, it becomes clear immediately that to prove such a theorem, you really have to prove the contrapositive, right? I mean, you have to show that if something there fails, then you produce an efficient algorithm for factoring. That's the only way. And in fact, that's what I'll try to show you in some of these cases. I'll hint it to the ideas. And try to show how to form some things that don't look at all relevant to factoring, get efficient factoring algorithms.
Is there a reason you chose that axiom and not a reasonable axiom?
Yeah.
Like one which is the problem that we believe might be like. Not everybody believes that.
Of course, yeah. Just to illustrate, yeah. Yeah, I chose this because it gives the largest variety of consequences, but there are other axioms that imply other things, and there are statements about this concept that have nothing to do with the assumption. I've chosen, I only have 50 minutes. Okay, so here's, I think, that perhaps the first example that should be given of this type about something that is not related to factoring in an obvious way, implies an efficient algorithm for factoring, is this toy problem, which I'm sure a lot of you know because of the famous four-color theorem. So here is a planar map, like we know in geography books, and we want to color the countries in such a way that no adjacent pair of countries get the same color. And in fact, this one is, we can do it in, here's a coloring of it in 4 colors. In fact, that I showed you a nice proof that it has a 4 coloring. But this doesn't shock you exactly because you know that every planar map has a 4 coloring. So as a function of the map, it's not really interesting. But if you replace 4 with 3 and you ask, does this map have a 3 coloring? Well, the answer about this one is no. So actually, it's an interesting function. And it's an interesting function. We can ask ourselves, what is the complexity of this function? How long does an algorithm that tries to solve this problem takes? Okay? And the first statement about factoring that I don't know if you've seen, and maybe it surprises some of you. If you have an efficient algorithm for factoring, if you have an efficient algorithm for coloring maps in 3 colors to decide whether it's possible or not, then you have an efficient algorithm for factoring. So here, yes. So you know the answer because, yeah. So exactly, I mean, this is exactly the kind of thing that you remarked in the previous talk. After you know everything, after all the proper definitions were made and their content, their philosophical content was understood, then it becomes a triviality. So let me explain this triviality. This follows from NP completeness, and NP completeness is probably the mother of all fundamental insights of complexity theory. And there are 3 parts to what will go on here. First is the NP as something as a class that captures theorems for which we have efficiently verifiable proofs. Then the notion of efficient reductions between problems, and third, the completeness. And here are the 3. The definition was given, a function is in NP if whenever the function is 1, you can verify it using a fixed polynomial time efficient algorithm given a witness that's not much longer than the statement itself. And it is trivial to see that 3 coloring, for example, is in NP because I just showed you. If I showed you a 3 coloring for that map, it would be a easily verifiable proof. Factoring is in NP. And so both problems are there. The next statement, which relates to this theorem, has to do with the relative difficulty of problems. Okay, so we define this partial order on computational problems, which is fundamental. We say that f is less than or equal to g, and you should read it f is easier than g, or not much harder than g, if there is an efficient algorithm for f that can use as black box answers for g. So it's clear now that if we had an efficient algorithm for g and f is less than g, we also have an efficient algorithm for f. So what we are interested in showing is this inequality, right, in this language. This partial order is fundamental because it tells us the relative difficulty of problems, and it becomes even more interesting if, well, of course, this partial order is transitive, and it becomes more interesting when you look at the maximal elements under this partial order of various complexity classes, okay, in particular in NP. So you say that a function G is complete, a function in NP is complete, if every other function in NP is less than or equal to it. A very natural definition. What's not so obvious is that this problem that I mentioned, 3 coloring of planar maps, is NP complete. So in some sense, with this one single problem captures the difficulty of this whole class, and in particular of factoring. So if you understood that, then you, of course, conclude immediately from this that factoring is easy, given the fast algorithm for 3 coloring. And NP is, as I said, is the fundamental idea, and well, probably it's most understood by lots of people. Let me just say this about it because I want to get into more recent stuff. That, I mean, one thing that you probably know is that satisfiability and coloring are not the only examples. By now, there is a collection of huge a number of computational problems from a variety of areas in science, in mathematics, algebraic problem, combinatorial problem, logical problems, all of which are NP-complete. So if this axiom was true, if factoring is hard, all of them are computationally hard. And I should say that, 20 years ago, when you proved something was NP-complete, it was usually an excuse to your employer that, in some software company, that you can just not solve this problem anymore. But today that we understand that it's a pretty good excuse for mathematicians not to try to prove a theorem, because usually if the problem you are working with, you can associate with it a computational problem which is NP-complete, and in fact quite a few of them are known today, then it means that structurally it's difficult. It's hard to prove structural theorems about this, whatever world it is. So it is, I think, interesting for those working in, well, if you want excuses, you can use this one. I think it's just a fundamental concept, and it will serve us for a long time. But I wanted to switch into more modern implications of this hardness of factoring, and by far the most well-known is cryptography. So in order to understand why and how it is related to cryptography, and sort of answer Peter's question, why did I choose factoring, for example, and not recoloring, is this absolutely unique feature of factoring, which is shared by only a few other problems that are natural that we know, is this, the inverse of factoring is multiplication, or the inverse of multiplication is factoring. So it's a very interesting function. If you start with 2 primes, P and Q, it's very easy to multiply them and to get the product. When you start from the product, then you have the factoring problem to get back to this pair. So somehow we already see that when we look at things computationally, we really have meaning to this hard and easy. Then there are 2 objects here, P comma Q and P times Q, which information theoretically are absolutely the same. They have the same information content. But computationally, it's easy to go in one direction, it's hard to go in another direction, and this was just suggested by Diffie and Hellman in their seminal paper in '78, to use this as a foundation of cryptography. And so the computational glasses enter here in saying that whatever cryptographic problems, whatever things we want to deal with, elections, you name it, I have a few examples here. Whoever is going to participate is bounded computationally, can do only probabilistic polynomial time computations. And then you assume this, and then you try to use this assumption to solve important problems. Now, the basic 2 problems that always interested cryptographers since, it's more than 2 millennia, probably around 3. People have been working on these things, is how to, mainly the first one, how to encrypt messages, how to hide information from other people. And another one is signature or authentication. And people really started playing with these concepts with just this assumption, and the assumption that this is indeed easy and this is indeed hard, and everybody is bounded polynomial time computation. Try to solve various problems that the digital world arose or suggested. In this world, the people that participate in don't sit around the table and are using some cards to play poker, which are, have opaque backs and you cannot see what the other guy has. This is a digital world. The only thing that, the players are computers and they send information across. There are no physical means to hide information. It's purely digital. Okay, but they did suggest ways to do this, and then it continued this coin flipping, oblivious transfer, lots of problems. In fact, playing poker was like a benchmark for a while. Then it was done. one of the problems that was really hard for a while was this 2 millionaires problem. That I'll, let me define it for you. I mean, there are these 2 millionaires who want to decide who is richer. And this is the only bit they want to come out of the conversation. They don't want anybody, they don't want the other side to have a clue of their wealth. Is this possible? Okay. This was standing there for a while. In fact, you can look at a special case of this where these millionaires, either have a million or don't. So just a Boolean case, and then it becomes just the OR function. And even then, you see that it's a very difficult problem. They just want to decide whether both of them have a 1 or something like this. Even then, it's really difficult. Not only is it difficult, you easily convince yourself that in the information theoretic world, it's impossible to solve without revealing information. So, but once this was solved, in fact, sort of immediately with it, everything was solved. So I'll try to explain what, well, okay. Everything means so let me just say it, any problem you can dream up, okay, in which some party is involved that want to compute something and they want to hide information in certain ways. Like poker is quite a sophisticated example. You have to deal the cards, and then you have to distribute them, and then people have to be able to exchange cards. And you want to do all of this digitally without, just the way it should be. All this is possible. So of course, I'm not going to explain how this is done. What I want to say, another idea of, that you've actually seen, this completeness idea and reductions enter into making the jump from here to here. Okay. So the first idea that was actually evident already in the first papers is that this function, factoring or other one-way functions, can serve as some kind of a digital envelope. I mean, you can think of the pair P, Q as something, information in the open, and their product, which determines them, is this information in an envelope. You cannot, you see it's sort of committed to, but you cannot really understand what's in there, It is encrypting only P times Q and not a product of other 2 primes because of unique factorization. And in fact, this idea through works of Goldwasser, Micali, and Rabin, RSA, various suggestions here to actually implement keeping secrets in envelopes, not only when they are products of primes, but even when they are single bit, you can do this. So that was the first fundamental idea, that you can use this assumption, this axiom we have, as a digital envelope. But the way in which this millionaires problem led to a solution, let's say at this point I'll show you everything is everything when you want to compute an absolutely arbitrary function. So we have these 2 players. They each have a secret. Alice has X and Bob has Y, and they want to compute this function. For example, is X greater than Y? It's a millionaires problem. How do you solve it? Well, the important thing about computation is we know that it consists of atomic steps, so we can write this function. Well, of course, this function has to be efficiently computable, otherwise they have no choice. So, but if it's efficiently computable, it can be described by a small Boolean circuit. So maybe X is n bits and Y is n bits, and you go through this process of n's and ors and nots, and you eventually get this function. And you look at it and say, if you want to solve this problem, first of all, you have to solve the OR function, the single bit function, because it's it's part of this computation. So that's what Yao did, in fact. He solved it. He showed that the millionaires problem with 0, 1 input is solvable because not only can you put bits in envelopes, you can actually compute with the envelopes. You can have a mechanism, a protocol by which each party enters a bit in an envelope, and out comes an envelope with the OR of these 2 bits. And it still, has the same, does not reveal anything about the content, but you have manipulated it into a new envelope, which contains the OR. And once you have this, and is the same, and negation is easy, you have a procedure, because now it's a complete problem. When you can do it once, you can do it polynomially many times, and you can evaluate, you can compute any function. In fact, you can go from functions to, to more complicated things like games and partial information. You can, even defining these things is not easy. I should say here that, yeah, maybe I just want to make sure that I don't get across the idea that these things are simple. I should have stressed in the beginning that in all this big list of problems, in particular in cryptography and in randomness, the very definitions, we understand them today, and when you look at definitions, they look reasonable and they capture what you want. Many times in the evolution of this, there were lots of alternatives, and it wasn't clear what is the right one. And it's very important that you pick the right one. And then not only do you get the really right meaning of these notions, but you can actually prove these theorems, which in other definitions will be trivial or wrong or both.
Why do you call it oblivious? So
Good.
Is it required to have just prime the composition or it is A and B problem?
No, and they are bits. They are bits.
No, when you solve it, you use prime.
I didn't say how. I said that people solve this problem of how to use the hardness of factoring into.
Yeah, but if you take another hard problem, can you also there is some special?
There are some. We'll see in a second. Okay. Yeah. So I'll talk about this a little bit. Yeah. What was your question?
Why do you call it oblivious?
Yeah. Why did I call it oblivious? Oblivious. I just meant that maybe it's not the right way, but it's the right name, but that's how it was called at the time. Maybe it should be called computation in the dark, in which these people are talking to each other and manipulating this. They're actually simulating this circuit, and they don't know what they are doing. But nevertheless, they are doing something meaningful, and at the end, they get the right answer.
But they don't see the symbols of each other. Machine does.
No. This is not the protocol. I just wrote. I didn't tell you the protocol. I told you, first of all, a function can be computed by a circuit. Second, Yao proved that you can implement such a gadget. Third, you can compose this gadget according with the circuit. So the protocol will involve doing this lots and lots of times, as many times as the gates in the circuit. They would have to do it, and each one is a little protocol. But at the end of this, so they will simulate the circuit.
In the middle, they don't see input of each other.
They never see inputs of each other. They just see these envelopes.
The point you can compute function, you distinguish them and it doesn't revealing x and y.
Exactly.
And function is 0 or 1. So
Exactly. Yes. Exactly. And this is not easy. So even this protocol is, requires lots of the ideas that came out before, and even just the very encoding of the input in these envelopes requires the oblivious transfer of Michael Rabin, and lots of other ideas have to go in. This is a complicated theorem if you want to make it, completely rigorous. Okay, so another thing about this, I want to say that this problem and this oblivious function computation is difficult even if the two players do exactly what they are supposed to do. They are doing exactly what the protocol of Yao tells them to do. Of course, this is not the world we live in, right? I mean, the world we live in, we don't trust each other. So the other important issue of cryptography, and Michael Rabin will talk about this more, is the question of, this ultimate dilemma of cryptography. There are two issues, privacy and fault tolerance. You want to protect your secrets, and on the other hand, you don't trust the other party. So, you can always, give up one, tell the other part, tell me your secret, I'll see that you are doing what you are supposed to do. So, for example, almost every protocol in ancient cryptography starts like this. Choose a pair of prime, multiply them, and advertise it in your web page. Okay? That's the beginning of almost every protocol. So if Alice is supposed to do it, she says, here, I did it, and then, Bob says, really, how do I know that's what you did? And maybe doing something else will force later a revelation of some secrets of Bob. So he's not willing to believe it. On the other hand, if he'll get it, he'll get into our bank account. So how to solve this dilemma? In fact, it exists in mathematics too, It's well, everybody has their favorite incidents in the history of mathematics in which the end of this was not a promotion of Alice, but rather an early publication by Bob. So if you are in this situation, you can contact me. So what do we want here? I mean, we want, obviously, I mean, in these examples, we want a zero-knowledge proof. We want to be able, Alice, in both cases, wants to convince proof that the statement she's making is true in a way that will reveal no information to Bob except for the truth of the statement. Very simple. Obviously impossible. So in the computational world, it's not impossible. So in a paper with Goldreich and Mikali, we proved that some statements have zero-knowledge proofs. In fact, the statements I showed you, if a map is given to all of us, it's on the board, I can not only, we know that there is a short proof that this map is three-colorable, I can give you the coloring, but in fact there is another way in which I can talk to you, and that's an interactive proof. I will not get into the definition. There is another way in which I can convince you that this map is three-colorable without giving you a hint about anything about the coloring and a hint about anything else you didn't know before. Why is this interesting? I mean, we wanted to prove GRH, not three-coloring of maps. Who cares about it? But, we already saw that. And in fact, this protocol uses the properties of this problem, three-coloring, obviously, the nice locality of neighboring countries and lots of, specific things to three-coloring. We use it in the protocol. However, because it's complete, because of the theorem if you look at the Cook-Levin theorem of the NP completeness, what it means, what it actually means, it really means that. You don't have to think about NP completeness. It means that there is an efficient algorithm A that will transform any mathematical statement, fix your formal language, any mathematical statement into a planar map. And both Alice and Bob can do it to the GRH, for example. GRH corresponds to a map and not much bigger, an efficient algorithm. And they all know this algorithm. Moreover, the same algorithm will transform any proof in the same formal theory into a three-coloring of M. This is the content of the NP completeness result. Okay? But listen, I mean, if Alice wants to prove to Bob that she knows the proof for the GRH, all they have to do is move into this world of three-coloring maps. And all she has to convince him is the map they both generated is three-colorable. And this means that every theorem that has a proof has a zero-knowledge proof. Okay? Yeah. Yeah, the map depends only on the length of the proof. I should have said the length, or not on the proof. Yeah. So, right. So. Of course, you have to say that my proof is only 200 pages. Yeah. Otherwise, I wouldn't talk to you anyway. So, this is what I want to say about cryptography. And now I want to talk about randomness, which is the other big issue here. And in fact, I just want to say beforehand that those two subjects and their computational versions developed sort of together, and they really fertilized each other in really absolutely beautiful ways. And in particular, some of the definitions that I'll show you were essential, like in your question, to really define what it means for an envelope to hide a bit and so on. Okay. So the again, a very, very basic question of, that people ask themselves very ancient times is what is a random object, or when is an object random, or when is a distribution random. And we complexity theorists, will say, like we say about every other concept, that this is a computational concept. Okay, so randomness has to be defined computationally. One of the nicest illustrations I heard of this is that if I took a coin out of my pocket, and I flipped it in the air, and I asked you to decide when it was at the peak height what it will come out to be, your chances of guessing it right would be about 50-50. Okay, it's sort of clear. I mean, let's say the coin is unbiased, my hand is unbiased, I'm not a magician, and so on. And on the other hand, if on top of this video camera there were, I don't know, 20 other video cameras looking at this coin in all directions, and these were all hooked to several Cray machines, then clearly by the time the coin is in the air, these computers will actually determine completely what it will be when it lands. Okay? So whether this is random or not really depends on your computational power. And this idea came into these definitions that are going to say what we mean when we say that probability distribution is random. So let me make some definitions. We look at probability distributions over, let's say, binary strings of length k. So let me just define what the test is. Sometimes it's called a statistical test. Of course, it's just a function. So t is a function on strings of length k that sends them into 0, 1. And the test applied to a probability distribution is just a probability that under this distribution with the test t will say 1. Okay? Under the uniform distribution, under the distribution d. And maybe I should say that we will always U sub k is a uniform. Is a uniform distribution. Of course, our prime example of a random distribution is a uniform distribution. Okay, the question is what else is random? And the way information theory answers this is, well, we define this metric, which is the variation distance, which is the same as the L1 norm. It's just the maximum over the test of the difference that the T of D and T of D prime, let's say between two distributions, D and D prime. Okay. So what is the event that will separate them most under these two distributions? And we will probably say that D is random or almost random, if it's very close in the variation distance in L1 to the uniform distribution. The way we look at it is we allow only efficient tests. Because look, I mean, we can only implement efficient tests. We can only run a polynomial time algorithm on this distribution and decide and say, yes or no. That's our world. That's the only thing we can do. So the distance we define, the computational, if you want, variation distance, is the maximum when it ranges only over efficiency, like the polynomial size circuits or something like this. Okay? And this is a definition of if this is small, if in this metric the distance is small, then we say that the two distributions are indistinguishable, are computationally indistinguishable, because they cannot be told apart. And in particular, a distribution is pseudo-random if its distance to the uniform distribution in this metric is, let's say 1 over polynomial. Okay, it goes faster than 1 over polynomial. Then it's pseudo-random. It's pseudo-random because to us it's like random. We cannot tell it apart from random. Then it's random.
Maximum over all t's alone.
Yes, maximum over all t's, but t.
But then you run with big space anyways.
I didn't say it's easy to compute. I just defined it.
Even with this efficient function, it's still long to compute.
No, I don't care about how difficult it is to compute this function. I just defined it. It's well defined. Okay, and it's probably difficult.
It's efficient test. The test even efficient still takes like infimum of t's. Yeah.
I didn't say the maximum. T is efficient. T is an efficient circuit. Okay, yeah. For every t, this difference is well defined. Now take the maximum over all efficient tests. There are lots of them. I don't want to speculate how difficult it is, but it's well defined. Okay, good. In a similar way, sometimes it's easier to talk about, in a similar way you can define computational entropy if you want. You say that something is pseudo-random if its computational entropy is roughly k minus 1 over polynomial. The main question is, you can make all as many definitions as you want. Is it meaningful? I mean, do you get anything new? That's the question. And the answer is, a huge yes. There are probability distributions whose real entropy is much, much, much smaller than k, which are nevertheless pseudo-random. They look random to us. This is what I'll show you in a second, the outcome of the work of Blum-Mikali and of Yao. Okay. How do you build them? Of course, again, it's a complicated process, and I'll try to make it simpler than it is. But, well, we want to increase computational entropy. So let's look at our assumption again, and let me write it differently now about the hardness of factoring, because these are the only essential features I'll use, and in fact, they are sufficient. And it's just easier to write it this way. We have a function from n-bit strings to n-bit strings, like multiplication, which is easy in one way and hard in another way, in the other direction. And let's specify what hard means. Hard would mean that that it's, at least sometimes it is hard to compute the inverse. So when you take a random x and you give an efficient algorithm f of x, the probability that it will give you x back is not 1. It's 1 minus something noticeable, 1 over n to the 10. That's the assumption. And if you have this, then it's sort of obvious, even though I didn't make this definition, it's sort of obvious that there is something going on, right? We know that when we are given x, it's easy to compute f of x. So even computationally, you learn nothing new. There is no randomness in f of x given x. However, given f of x, there is some information about x, computational information. And from this, it's clear that it's at least something like log n. So somehow you would like to say maybe the joint distribution x f of x has more randomness. But of course, this is nonsense, because it cannot depend on the order. We can look at x first. How do you get out of this? I mean, you still want to extract it. And the way to extract it is actually to look at a harder function. No, it's most 1 minus delta. Yeah. No, actually, it's OK. But let's not argue about this. It's OK. The way to make the function harder, this is another fundamental notion of complexity theory, is this hardness amplification. You can make somewhat hard functions harder than they really are. So in this specific instance, what is true is that because it's hard to determine x, there is some feature of x, which is just 1 bit, this Boolean function b, okay, which takes n bit into the numbers and produces 1 bit, which is sort of extracts the hardness of f. So what does it mean? That whenever you take an efficient algorithm and give it f of x like before, the probability that it would get this feature of x, b of x, is at most half plus epsilon. Okay, epsilon is again tiny polynomial fraction. This is universal, in fact. It's the theorem of Goldreich and Levin, which of course Yao and Blumenthal didn't have, but they had something else. So it doesn't matter. It's really interesting. This function does not depend on f. You can do it to any f, not just to factoring. You can always, there is always a hard core of any somewhat hard function. But once you have this function, then, your guess, instead of publishing f of x and x, you'll just publish f of x and b of x, this feature of x. And now it sort of stands to reason that even though this entropy here is just n, the computational entropy, just by the statement here, is n plus 1. Okay? It requires a proof, but the proof is not difficult once you have this. Of course, the proof of this theorem is, again, a reduction. We assume this is hard, and we prove this is even harder, but the proof actually says, suppose I had an algorithm for that, I would construct an algorithm for that. And the proof is actually very interesting, and it involves a Fourier transform over GF2 to the n, but I'm not going to say much about it. What I want to show you is what to do with it. So we somehow increase the computational entropy by 1. That's great, because that's what we wanted to do. So let's just look at it like this. We have a pseudo-random generator. So this process takes a uniform distribution on n bits. This is D0, and builds from it, efficiently builds from it f of x, b of x, which is an n plus 1 string, whose computational entropy is n plus 1. It's indistinguishable from random. Now, if you ask any millionaire, they'll tell you that it's only hard to make the first million, and then actually, you go into your, you are probably mostly in math departments, but you go to your computer science department across the hall, and there will be millionaires there, so you can ask them. So what you do is just you repeat, you just repeat it, you know? You repeat it again and again and again and again and again. And you can increase the entropy as much as you like, almost, okay? And of course, again, there is another reduction to prove that indeed, if you could, you know, distinguish this from random, you could, you know, something was wrong back then. But this is actually works, and this is exactly the Blum-Micallin-Yau procedure. And this generator, which expands randomness, is an efficient procedure. And you can expand it as long as you like, or as long as you like. This K is roughly the complexity of inverting F. Basically, well, this is what it is, the complexity of factoring. So this leads to really amazing consequences, and I can only touch on them. Here's one. You know, that we discussed, you know, Michael Rabin will talk about public key. I wanted to write private key. Public key cryptography, but private, the old-fashioned way. You know, when these two agents are meeting and they are exchanging the Book of War and Peace because they want to, you know, exchange lengthy communications. This is supposed to be their random pad. But now they can exchange the Reader's Digest version of Tolstoy, which is just 20 pages. And they expand it using this generator, and nobody can tell, because if somebody can tell, then this wouldn't, you know, the assumption would be violated. Excuse me?
That method will give back War and Peace?
Yeah, no, it will not give. If you start with random, it will give, yeah, but just, yeah. If we thought of War and Peace as random, then yes. The Reader's Digest. You can actually do even more wonderful things, like construct pseudo-random functions, and unfortunately I cannot talk too much about this, but not just long strings, but random-looking functions whenever you evaluate them only in polynomially many points. And if you have these objects, you know, it's still under the same assumption. If you have this object, then it's, for example, clear that you cannot learn, you know, what a function, if function describes a concept. And these are natural functions because they are defined by efficient procedure. You cannot learn a pseudo-random function because you cannot distinguish it from random. So it's, you know, with the right definitions, becomes obvious. Another consequence is what Sasha was talking about. We are trying to prove lower bounds. We are trying to prove that, you know, factoring is hard. But we know random functions are hard. Random functions require large complexity. How can we distinguish, using feasible methods in his definition, how can we distinguish a random from pseudo-random function using feasible methods? It contradicts this construction again, okay? So it leads to, you know, he has these wonderful theorems he had no time to talk about, which, you know, sort of say essentially this. But the most fascinating application, and this will be my last slide, is that where do we use randomness most, at least in, you know, in applications? We use it in probabilistic algorithms, right? So why not use this? I mean, what does it say? And this was the fundamental observation of Yau in his paper, that once you have pseudo-random generators, this means that computational randomness in algorithms is weak. You know, if you have an efficient algorithm, what is an efficient probabilistic algorithm? Efficient probabilistic algorithm is, you know, takes the input z and it tries to compute whether, you know, h of z is 1 or 0, you know, just whether it's prime or not, for example. So it tosses some coins r of, let's say, k bits. And then, you know, the property of the algorithm is that almost always it gives the right answer. Okay. But why feed it a set of, you know, a sequence of random strings when we can, random bits, when we can instead feed it the output of this generator on a much shorter random string, just n instead of k. Then, rather than deterministically simulate this algorithm by trying all the 2 to the k possibilities, we can try just the 2 to the n possibilities, which is much fewer, right? And we still distinguish between the yes and no cases, okay? So computational randomness becomes, you know, it depends on your hardness assumption. You know, if factoring is not in polynomial time, you can take n to be k to any epsilon you like. And then every probabilistic algorithm, like the primality, but any other one, can be simulated deterministically in sub-exponential time, much better than the trivial one. You know, if this problem, like what we currently know about factoring, requires, you know, at least 2 to the n to some constant, maybe not a third, but 1 over 100, we can take n to be some polylog in K. And then this will be almost polynomial. And in fact, if factoring required really 2 to the constant times n time, then RP would equal P. Computational, every probabilistic algorithm that runs in polynomial time would be able to simulate it in deterministic polynomial time. There's no use for randomness in this sense. Okay. Of course, you may, you know, well, what is this assumption? I mean, we know that it's false, but you know, this technology, this is not the end of the story. I mean, there are other generators. There are other generators that, if I find the slide, yeah. That Namnisan and I constructed that are, you know, in many cases they are totally uninteresting because they give you an increase in entropy, but you do it in unreasonable amount of time. This algorithm G becomes inefficient, and the applications, for example, to cryptography and to pseudo-random functions disappear. Yeah. However, it still works for the randomizing algorithms, and so instead of this axiom that I suggested there, you can put other axioms. You can assume that satisfiability is hard, or that the permanent is hard, that the P is different than NP. They will all give you that randomness is weak. And of course, here you can expect to find things that are exponentially hard. So probably randomness is weak. I mean, that would be my conjecture. Okay. So, for okay. Here's my. So I just want to conclude with this easy open question.
Are you suggesting that you believe that axiom?
No, but I am suggesting. But I don't need this axiom for randomness is weak.
No,
No. The factoring, I have no idea. No. I don't say anything about factoring. But the fact, but I do believe that this natural.
Axiom, usually that would mean that somebody believes.
Oh yeah, but you know, you should try. You know. Yeah, but of course, prove any lower bound is the real. But you know, I know that you are not going to try to prove this lower bound. So I want to suggest that it's really a mathematical problem. You don't have to know anything about Turing machines. You don't have to know anything about computation. Here's a way to express this lower bound question in terms that I'm sure all of you have thought about. You know, there's a very natural reduction between functions. Let's say these functions are polynomials over some field. Okay, this is a projection reduction, right? We say that one polynomial is less than or equal to another polynomial if you can use a linear transformation to transform the variables of one into the variables of the other. And then you compute the other function. You know, that's just whether you have the same function on a affine subspace. It's extremely natural. Now let's look at these two familiar functions, the determinant and the permanent. Let's say determinant on n by n matrices and the permanent on m by m matrices. It turns out to be a theorem that determinant on n by n matrices reduces to permanent on n squared by a squared. There is an efficient polynomial reduction. Now, if you have a black box for permanent, there is even this linear reduction from determinant to permanent. This makes sense in the other direction, only it's not so efficient. You can play with it and figure out that you can put permanent into determinant if you exponentiate the number of variables. Okay. Try to prove that there is no better way to do it. You know, that whenever you do it, you cannot increase the number of variables just polynomially. Okay. If you do, this will, you know, we have all the other machinery. It will already essentially separate P from NP. That's it.